we have such assumptions in place. Okay. Finally, so we will simulate and we will characterize. Okay. So let's come to dynamic power. So one thing that we need to understand is, or what we already agreed on, is that the energy stored in a capacitor is 1/2 CVDD square. Am I right? Hello? We've already agreed on this.
Yes, sir.
So, however, the energy drawn from the supply is, if you want to charge this capacitor from 0 to VDD, the energy that is drawn from the supply is something like this. So what has happened? Only half the energy that was expended has been saved, has been put on the capacitor, has been conserved in the capacitor. The remaining half has been dissipated in the resistance, the channel resistance of the MOSFET. Are you able to see this?
Yes, sir.
So now when this capacitor CL switches from 1 to 0, now that remaining 1/2 CVDD square will also get dissipated. Where will it get dissipated? In the channel of the NMOS. Are you able to see this? Hello? Is this clear?
Sir?
Yes.
Sir, I'm like I into VDD into DT. I should be input current, sir.
Sorry?
I of T should be input current, right, sir? And like if you're talking about the energy drawn from the supply.
Yeah, so we are modeling that input current as the rate of charging of the capacitor. It is rate of change of charge on the capacitor.
But our capacitor is our output capacitor, right, sir?
Yeah, but that is what you're charging, na?
Sir, here input ka matlab VDD. Is that VDD or our input V in? Because I can't see any connection between input and output directly so that my current can flow.
So does a current flow between input and output in a MOSFET?
No, sir. I'm like.
So why should there be a direct connection?
Sir, yeah, sir. My doubt is that here the drawn from the supply means VDD, right, sir?
Yes.
Okay, sir. Okay. Thank you. Yeah, that was my doubt. Yes.
Yeah. So if you look at the waveforms, suppose you gave this kind of an input. So you've all done these inverter simulations, all of you have done. Just now go back and look at your waveforms there. If this is the kind of input, you will see that the output is, something not exactly that sharp. You seen that?
Yes.
And now if you plot the current through the PMOS and the current through the NMOS, you will see that PMOS and NMOS have currents at the peaks of currents at different times. Over here, there is a small short circuit current ka peak. But largely then the current is flowing from the NMOS when the output is falling and from the PMOS when the output is rising. So most of the power dissipation is happening in the PMOS on the rising side and NMOS on the falling side. And in terms of current consumption, you will see that the current consumption is following this kind of a curve, where it is IP minus IN is being plotted over here. Okay, and you will see that power from VDD will happen only during the rise cycle. But energy from VDD, because power is consumed only during the rise cycle, from VDD, the VDD energy also gets consumed during the rise cycle. And the energy stored in the capacitor first comes to half VDD, half CV square, then falls to 0.
So can you come to the current graph once?
Yeah, I'm already there. Please tell me.
So below one, the second row, second column, third row.
Okay.
Yeah. So sir, what we're plotting here, sir?
This is the current of the capacitor. The current that the capacitor is seeing.
So this equation is not visible actually. So can you?
It's IC is equal to IP minus IN. Current from the PMOS minus current from the NMOS. The NMOS will take away the charge. PMOS will deposit the charge. Therefore, current charging the capacitor is just the Kirchhoff's law over here. In this particular system, we're just applying Kirchhoff's law.
Okay. So why the current is rising initially? It should be maximum, then it should fall, and then it should again fall, rise again.
Why should it rise? The direction has changed, is it not?
No,
when
no,
the
sir.
capacitor is discharging, the direction of flow of current has changed. So it will appear as negative current.
Okay. So it's like, okay, the plus and minus. So, but when initially it is charging, it should be falling. The current should fall, right? Because current will initially be falling, right?
Yeah, so current initially would rise and then fall.
Okay, it is fall.
Once the capacitor starts to get charged, the current would fall. That is why current fell.
Then, so when it is dropping, the x-axis, what that point is, sir? Can you say? When the current curve is crossing the cutting the x-axis for the first time, what that point is basically?
When the current is in the third graph?
Yes, this is second column, third row. Yeah.
So when,
yes, sir, when it first cuts the x-axis, the current curve only, and then there's a time lapse, and then it rises. So I'm just wondering to know what these points are, sir.
The time lapse is the time gap between the fall and rise of the input. Because at that time, there is no current flowing anywhere. The CMOS, it's a static CMOS circuit. It's a static CMOS circuit. You see that?
Yes, sir.
So in a static CMOS circuit, when there is no transition happening, we don't expect any current to flow.
Yeah.
So that is what we are looking at there. But there's no current flowing in that duration. Is that okay?
The slide gone.
Yeah, it's coming. Give me a moment. But are you able to see that in the static CMOS, there is no current in the intermediate part when there is no toggling happening? Hello?
So this region I'm not able to get exactly. I mean, in the curve.
This region. So you tell me, what is happening here? Is there any change in the output voltage happening here?
So voltage of capacitor voltage.
Yeah. This is V out, no? Is there any change in output voltage happening here?
No, sir.
So if there's no change in output voltage, why should there be current flowing from either the PMOS or the NMOS?
Yes, sir. Yeah.
So that is what it is reflecting.
Okay. Okay, right. Okay, that is 0. Okay.
Okay.
Yes.
Okay. So what essentially we are saying is that the total switching power is CVV square into frequency. Why frequency? The number of times that the circuit switches. That many toggles will happen. 1/2 CV square when the output rises, when the output falls, 1 by 2 CV square when the output rises. So per cycle CV square and multiplied by number of times it would toggle in a second. So frequency. Are you able to see this?
Sir, so this becomes the average dynamic power dissipated.
Average switching power, not dynamic power. Dynamic power will also have short circuit current in it.
Okay. So, sir, this is what we have to do in our assignment, right?
Yes, you have
Average
to do this.
Power dissipation.
You have to do this. You have to also include the short circuit power in it. But yeah.
Okay. So in a single clock, means where we are going from 0, 0 to 1, 1, we have to take in account the whole current waveform and integrate with it by multiplying the voltage.
Yes. Okay. So what does this SSW represent? So SSW represents the frequency multiplied by alpha, where alpha is activity factor. Okay. For a signal that is a clock, alpha is equal to 1 because clock toggles 0 to 1 and 1 to 0 in every cycle. But if there is a signal that switches only once per cycle, alpha would be 1. If there is a signal which has a glitch, what would alpha be?
So in one clock cycle.
1 by 2, sir.
Yeah. So there's a glitch in every clock cycle. So what is alpha for that particular circuit?
1 by 2, sir, as it's raising and falling.
For every rise, so any single switch, any signal switching once meant alpha is equal to 1 by 2. Over here, the signal is switching twice, isn't it? It is rising and then it's falling.
Then it's 1.
So
sir.
1. Let us say this glitch was spurious or not spurious, and finally the output had to rise. So what is alpha?
3 by 2.
1 by
3 by 2.
1.5.
So do you realize the challenge that glitches cause?
So how come the 3 by 2, sir? I didn't get it.
One transition, second transition, third transition.
Yes, sir.
All in one clock cycle. So clock is here. Let us say this is your adder circuit. Some node in your adder circuit. It had a glitch, carry out, let us say. It had a glitch and then it rose to 1. So what is happening? What is the glitch leading to?
So where's the by 2 factor coming? 3 is because 3 transition. By 2, why would be by 2?
Because every transition is 1 by 2. A clock, we say activity factor is 1. A clock has 2 transitions. So every transition is 1 by 2.
So say when you written, if the clock signals the clock alpha is 0, so alpha is activity factor, but alpha is 1 when we have 2 transitions. That is, yes.
And a clock has 2 transitions. In a clock period, it has 2 transitions.
Yes, sir. Yeah.
So if I say that is alpha, that is 1. If I say alpha for a clock is 1, then alpha for a signal which is transitioning only once would be half.
Yes, sir.
And if it is there's a signal which is transitioning thrice because of a glitch, alpha would be
3 by 2.
If there are 2 glitches, then
1.
5 by 2.
No,
So every glitch is a drain on lot of dynamic power. So we do not want glitches in our system. Okay. Glitches are a signal integrity issue, but they are also a much bigger power issue. Okay. So looking at short circuit current, what happens to the short circuit current? When the input is toggling, there is a time when both PMOS and NMOS are simultaneously on. which is when some current would flow from VDD to ground directly. That is short circuit current. This current is no longer we're not talking about CL over here. We're talking about directly VDD to ground. We are calling it as IVDD. Now, if the rise and fall times are good, then we can limit this short circuit power to less than 10% of total dynamic power. And therefore, for back of the envelope calculations, we can ignore this component. But when you simulate, you have to integrate. You will anyway integrate it. It will get added there. But for back of the envelope calculations, you can ignore this component. Is that okay? Rajneesh?
So, sir, when this Vout is charging from VDD via the PMOS, this short circuit glitch will occur. And similarly, when Vout is this CL is discharging via the below NMOS, then this short circuit glitch will occur.
Yes.
So, sir, so per transistor, this so what we learned in the previous slide in the activity factor, that glitch thing, that this is the same thing with activity factor 1.
So for every transition, there will be this short circuit current also that will flow. Okay. There is a charging current for load that we talked about in the previous section. That will definitely be there. Yes, but this short circuit current will also flow for every transition.
So, so this short circuit glitch, that alpha C VDD, that square, that here for this glitch alpha will be 1. So that this will be added in the total dynamic power.
But this is independent of C.
So
this is not dependent on the capacitance.
Yes, yes, sir.
So isliye purane wala, the earlier formula will not be applied here. That is what I want to correct in your understanding. That was a different topic. We were talking about switching power there. We are now talking about short circuit current. Both together make dynamic power.
Okay, yes, sir. Per transistor we have to add.
This is per gate, yes.
Yes.
Okay, this is not dependent on capacitance. It is dependent on rise and fall times.
Yes. Okay.
Okay.
Yes.
Faisal?
We need rise time and fall time to be as low as possible to reduce the dissipation, right?
Yes, to reduce this duration, yes.
Okay, okay, sir.
That is why you were given very tight specification when you were designing the first inverter in your assignment.
Yeah, yes.
Okay. So now let's look at that example. We say that we look at that 1 billion transistor chip. We know that to calculate power, we need to estimate some capacitance. So we go ahead and do something like this. For logic, 50 million transistors into 12 lambda. And we said that there is this per lambda, the width that we are talking about is 0.025 microns. That is a technology factor. And we said, okay, per micron, the gate capacitance was 1 femtofarad and drain capacitance was 0.8. So 1.8 femtofarad per micron. And I see that the logic capacitance is 27 nanofarad. Okay. For the memory, the devices go much more in number. The size is smaller. Therefore, the ratio is not as bad. It is coming as 171 nanofarads. And then we apply the dynamic power formula. We are ignoring the short circuit currents. As we just said, we expect it to be within 10% of this dynamic power. And we say that, okay, overall power consumption will be around 6.1 watts. Are you able to see this? Any questions?
Sir, what is this factor of a 25 nanometer per lambda?
That is, how much width do I associate with a lambda? One lambda, they say, is 25 nanometers. So
Okay.
there was this question, what is this lambda?
Yes, sir.
This is, they are saying 25 nanometers is this lambda.
Okay. Okay, sir.
They've just given the formula for that.
Yeah.
So what is this 0.1 and 0.02 in this calculation? These are like equation kind of thing.
You tell me, what were they? What were we talking about when we introduced the subject?
Some active factor or
Activity factor.
factor.
The number of togglings to expect. है ना?
So this 0.1 and 0.02 are the toggling factor for logic and memory separately, right?
Yes. Yes. 0.1 is the activity factor for the logic, and 0.02 is the activity factor for the...
Sir.
Yes.
Sir, as you said that if there was a glitch, our activity factor went to, it increased. Sir, but we are eventually multiplying this activity factor with the frequency. So, sir, if an activity, if a glitch occurs, then according to what I can see on a graph, my time period should increase. In that case,
Why?
Sir, because time period का मतलब ये है कि at a distinguished between a distinguished interval of time, the waveform is repeating.
That you will talk about in terms of clock. So how does presence of a glitch depend on clock period? Like how does a glitch constrain a clock period?
Sir, frequency means frequency means
I'm operating my entire device at only 1 gigahertz, na?
Yes, sir. Yes.
I'm operating my device at 1 gigahertz. How much time do you think a glitch would take?
It would take, okay, it would take less time, but
yeah.
Okay. I got confused, sir. Okay, sir. I'll look into it, sir.